Hello everyone, I'm Steve Cristaldi, Product Manager at Amphenol Ardent Concepts. I'm thrilled to be here today to share my passion for quantum computing with all of you. Over the next few minutes, we'll take a high-level look at the microwave cabling challenges and solutions involved in scaling today's quantum computers. The current generation of quantum computing systems is known as noisy intermediate scale quantum due to their sensitivity to thermal and electrical noise and generally lacking full fault tolerance. To combat these noise challenges, quantum processing units, known as QPUs, housing the delicate qubits, are encased in vacuum chambers and cooled to sub-millikelvin temperatures using dilution refrigeration technology. Coaxial cables are used for connecting essential components to and from the QPU and play a vital role in noise reduction within the quantum systems. In the quest for more practical quantum computers, qubit counts must exponentially increase while QPU sizes shrink. This presents both development and hardware challenges, notably in scaling microwave RF lines. The ideal solutions must balance mechanical density and signal integrity while considering thermal aspects for overall system success. Exploring the inner workings of a modern quantum computer, we find critical hardware components that enable practical installation and adaptability to ever-evolving architectures. While not explicitly depicted in this illustration, quantum computers critically rely on an abundance of room temperature control electronics, which are typically housed in a rack and stack configuration. These control electronics can come in various form factors, from traditional PXIe style designs to highly customized front panels, with all solutions geared towards increasing and maximizing RF connector density at the front panel. Establishing microwave RF connections within the quantum computer relies on specialized hermetic RF feed-throughs. These feed-through components maintain the necessary vacuum levels inside the cryostat chamber while serving as controlled impedance electrical transition points. As we move closer to the quantum processing unit, we encounter passive and active electronics. For instance, cryogenic attenuators filter RF signals and assist in thermalizing coaxial cables. Finally, the RF signal must interface directly with or near the quantum processing unit, necessitating the most compact and efficient solutions. These intricate components work together to facilitate the quantum computing process. As quantum computing systems predominantly use coaxial cables for microwave RF connections, they often employ pin and socket technologies like traditional SMA or SMP technologies. To ensure hermeticity, the electrical feed-through must include an epoxy or glass-sealed provision between the center conductor, dielectric, and body. The connector body must also maintain helium leak-tight integrity to the feed-through flange. In the image on the left, we see a hermetic electrical feed-through based on an O-ring sealed bulkhead SMA within a standard ISO flange. However, SMA's feed-throughs have limitations and require generous clearances for tools such as torque wrenches to facilitate installation and removal of coax cables. Modern quantum computing architectures require the greatest density, favoring a ganged approach, which eliminates housing and tooling clearance constraints. Employing epoxy-sealed connections further enhances density over O-ring sealed solutions. The advanced ganged hermetic electrical feed-through shown on the right represents a substantial density improvement over traditional SMA or SMP technology. In the realm of quantum computing, the transmission of RF signals to and from the quantum processor is a critical process, demanding the utmost noise control. This calls for effective filtering and thermalization through the application of attenuator circuits. These circuits offer tunable filtering capabilities, effectively reducing noise while ensuring proper thermalization of the RF control cables. As with the hermetic feed-through, traditional attenuator circuits rely on SMA or SMP technology. However, as we push the boundaries of quantum computing, attenuator architecture requires greater and greater density than what is available with traditional technologies. Again, a ganged approach can provide superior density through eliminating many of the mechanical bottlenecks associated with SMA or SMPM technologies. The ganged attenuator design shown here on screen can achieve an unmatched 2.54 millimeter by 3 millimeter signal density in a tunable format. When we examine the intricate hardware architecture of quantum computers, we encounter a critical constraint at the RF launch point to the quantum processor unit. These launch transitions at the QPU must meet extraordinary demands, including exceptionally high levels of electrical isolation over a wide range of RF substrates. Moreover, the connectors mating to the QPU must endure the lowest and most extreme temperatures on the order of millikelvin. To tackle the electrical and cryogenic challenges, engineers have embraced a solderless compression mount connector technology. This innovation provides a solder-free and electrically compliant connector launch transition, ensuring reliable mechanical integrity in the most frigid environments over multiple thermal cycles. Solderless compression mount technology also offers the added advantage of facilitating faster swapping of QPUs while reducing the overall QPU cost by eliminating the need for additional board mount connectors. As with previous components we've reviewed, a ganged approach introduces the highest level of density, particularly in the dimensionally constrained regions of the QPU. With quantum computing still in its infancy, RF connections to and from the QPU must also accommodate a wide range of form factors and material substrates. This is made possible through a wide array of channel counts and mounting form factors, allowing design engineers to position connectors as close to the quantum processing unit as possible. Gang solderless solutions then represent an indispensable technology in pursuit of achieving the density and performance needed to meet the demands of our exponentially increasing qubit counts and future chip-to-chip communication. By establishing a comprehensive ganged coaxial ecosystem encompassing solutions ranging from room temperature hermetic feed-throughs, attenuators, and QPU mount solutions, quantum computing designers can effectively scale qubit counts without encountering bottlenecks at hardware transitions. System designers seeking the greatest density possible can adopt a holistic system-level approach by leveraging an all-encompassing ganged ecosystem known as a top-to-bottom approach. The ganged ecosystem shown here is designed for immediate integration with mainstream cryogenic dilution refrigerator systems. The solution set can also be easily customized to meet specific cryogenic or vacuum chamber requirements. Designers facing more nuanced density challenges related to a specific hardware transition can opt for individual ganged components via an a la carte menu of options. Today, such ganged ecosystems are commercially available with a 2.54 millimeter signal-to-signal pitch with 1.9 millimeter coaxial-based versions in testing. While the ganged approach significantly boosts density over SMA and SMPM technologies, there are limitations based on coaxial cable size and construction when aiming for next-generation density. Let's dive a bit deeper into how the size and material construction of coax cables can impact our ability to develop increasingly denser ganged solutions in quantum systems. This is probably the most technical slide I'll have here, so just. Designers of quantum systems face an essential trade-off between attenuation and thermal performance. When it comes to coaxial cables, those without strict density constraints or without a large number of qubits might consider using a larger size coax cable to improve attenuation. However, large coax cables do bring with them increased thermal conductivity, which can result in higher heat loads at the quantum processing unit. As ganged coaxial developers, one of our primary considerations is the mechanical size of available coax cables when planning the roadmap for next-generation densities. Comparing common sizes like 047 and 034 semi-rigid, it's evident that smaller coax cables can provide greater flexibility for improving density. For instance, many designers today opt for the ubiquitous 034 silver-plated copper-nickel coax cable due to its balanced performance in terms of attenuation and thermal properties. However, as the number of coax cables in a given design increases, we reach a point where the combined higher thermal conductivity may risk the ability to maintain the QPU at the required temperature. With our current 2.54 millimeter pitch, it's possible to accommodate up to 1,500 coaxial lines in mainstream cryogenic refrigerators. Looking ahead at our 1.9 millimeter pitch solutions, we may be able to offer over 2,000 coax lines. You can see with that number of lines in the system at some of the thermal conductivity seen here, we start to encroach on the cooling capacity of mainstream cryogenics. Solving this challenge necessitates close collaboration between coax hardware developers, cryogenic manufacturers, and quantum system integrators to explore what is feasible in the quest for denser, more efficient quantum computing solutions. Today, quantum system integrators are grappling with increasingly formidable challenges associated with qubit scaling and the creation of truly fault-tolerant systems. As such, the quantum computing ecosystem is becoming more reliant on hardware manufacturers to develop infrastructure and their own expertise in cryogenically qualified and quantum-suitable solutions. Amphenol Ardent Concepts has made substantial investments in key areas such as cryostats, hermetic feed-throughs, and magnetic inspection equipment. The ability to provide cryogenic cooling to components is essential for designing and validating quantum microwave RF solutions. As we've reviewed, thermal conductivity and attenuation become critical factors for scalability. A more precise cryogenic evaluation regarding the impact of coaxial size and material properties is imperative. Another increasingly significant aspect is the development and characterization of non-magnetic connectors. Magnetic components and fields can disturb the delicate quantum states and operations of qubits, leading to decoherence and computational errors. The growth in qubit and QPU sizes necessitates positioning the connectors physically closer to the sensitive qubits. This slight increase in proximity to the qubit means that even trace amounts of magnetic elements in a connector can disrupt quantum processing. To address this, specialized equipment such as zero Gauss chambers provide nanotesla resolution and play a crucial role in accurately characterizing connector magnetism. While the majority of this presentation has emphasized density improvements achieved through ganged coaxial cable systems, the future of quantum computing demands even greater densities than coaxial cables alone can provide. As quantum systems evolve to become more fault tolerant, the performance offered by coax cables may no longer be essential. In the pursuit of truly commercial scale quantum computing ecosystems, reducing hardware costs is also paramount. Relying solely on coax cables is financially impractical, given the required number of qubits for commercial quantum computing. At the core of the ganged coaxial solution showcased today lies a dual-sided compression interface. This interface design is capable of delivering the necessary levels of electrical and mechanical performance without the need for coax cables alone. Consequently, a variety of different transmission lines can be integrated with this interface, enabling greater densities than coaxial cables can achieve and potentially offering more cost-effective solutions. This chart presented illustrates and compares some of the leading transmission line technologies under investigation as suitable mating architectures for the existing solderless compliant compression mount interface. While deploying non-coax-based solutions such as flexible PCBs presents numerous challenges, our investment in cryogenic development infrastructure and our long-standing focus in RF design provides us with optimism that solutions can be realized through time and effort. Today we've delved into a crucial aspect of quantum computing, the microwave RF transmission lines. We've explored how coax cables excel in providing the best electrical performance for noisy, intermediate-scale quantum systems. But as qubit counts increase, we face unique challenges. First, scaling up qubit counts means scaling up the density of supporting components, including coax cables, hermetic feed-throughs, and attenuators. The number of coax lines must grow, but this necessitates careful consideration of materials, weighing the electrical against the thermal properties. The concept of ganged form factors, such as the TR multi-coax, allows us to achieve coax densities down to an impressive 1.9 millimeter signal-to-signal pitch. However, the path to advancing quantum hardware isn't without its challenges, requiring investment in cryogenic vessels, leak detectors, and magnetic inspection equipment. In the future, quantum computing will demand more RF lines and density than traditional coax can provide. The RF transmission lines of future quantum computing ecosystem will be a marriage of density, signal integrity, and cost effectiveness. Thank you all for listening today. We've got about a minute left if there's any questions. Thank you.